In this video, I'm planning to prove that the integral of 1 over x dx is equal to the natural log of x, and prove that the integral of e to the x dx is equal to itself. And in order to do that, I'm going to start out by noting that e to the x and natural log of x are inverses. So the plot of e to the x looks like that. The plot of natural log of x looks like that. So those are actually printed on the opposite sides of the same card in the same place. 2. When x is approximately 0, e to the x is approximately x plus 1. So that is sort of in this region here. The e to the x function and the y equals x plus 1 function are pretty close to the same value. So I'm going to be using that in my proof. I'm going to start basically with the derivative of things and then use the antiderivative to prove the case. So first I'm going to start with the natural log of x. We will be taking limit of natural log of x plus h minus natural log of x divided by h as h approaches 0. That will be equal to some slope. I'm just going to write the slope like that. And going to go ahead and use a property of natural logs. I probably should have listed this in the assumptions. Natural log A plus natural log of B is equal to natural log of AB. That can be assumption 5. So when I do that, it will be natural log of x plus h divided by x. And I'm just going to say that's all equal to m times h. Then I'm going to use the inverse function, which is basically taking e to the power of both sides, using the fact that they're inverses. So x plus h over x equals e to the mh. See that I have taken e to the power of both sides. And now I'm going to use the fact that y equals m, or e to the x is close to x plus 1 over here. So that's mh plus 1. And I can divide x by x and get 1 plus h over x. And finally, subtract 1 from both sides. We'll have h over x equals mh. And finally, the slope is equal to 1 over x. So that proved that that dx, the derivative of natural log of x, equals 1 over x. And so now I'm going to use the antiderivative and say natural log of x equals integral of 1 over x dx. So I've shown that integral of 1 over x dx is equal to natural log of x. Now I'd like to prove that the integral of e to the x is equal to e to the x. This time I'm going to once again take the derivative. The derivative is going to be limit as h approaches 0 of e to the x plus h minus e to the x over h, and that's going to be our slope now. So when I take e to the x plus h, what can I do here? Oh, I can take this and turn it into e to the x, e to the h minus e to the x. So that is something else, an assumption that I could point out up here. 6, that e to the a plus b equals e to the a, e to the b. So then we will do e to the x times e to the h minus 1 over h equals m. And so h is going to be a small number, so I can replace e to the h with h plus 1. So it'll be e to the x times h plus 1 minus 1 over h equals m. Plus 1 and minus 1 cancel out, h over h cancel out, and so we will have e to the x equals m. So there was a lot of assumptions in this proof, but those are a couple of proofs. Oh well, now actually that was derivative of e to the x dx, ddx. Okay, so that's what the slope is and what that limit was. And to get the integral, basically take the antiderivative, e to the x dx equals e to the x. And that finishes up where we wanted to be. Now I have a mnemonic that goes DMS and IAD. And what they stand for is derivative, multiply, and subtract. And integrate, integral, add, divide. So setting up a derivative and an integral, the derivative of this derivative, multiply and subtract. So take the 3, multiply, and subtract. 3 minus 1 is 2. On the other hand, integral of x cubed, add, so I'll have x to the 4th, and divide over 4. In general, that works with negative exponents as well. Derivative of x to the negative 2, multiply, negative 2, and subtract, x to the negative 3. Integrate, add, so x to the negative 1, and divide, divided by negative 1, so that's equal to negative x to the negative 1. Special case comes up when you're dealing with x to the negative 1. Derivative, negative x to the negative 2. That came out fine. But what happens over here? Add x to the 0, and then divide by 0. Well, that divide by 0, it turns out, integral of x to the negative 1, as I just showed, is natural log of x. While I'm thinking about it, I want to do another example. Let's do the derivative of sine of, as long as this is in radians, then the line here where it's close to 0, this is the line y equals theta, whereas the whole thing is y equals sine theta. Meanwhile, if you do cosine theta, y is, this one is y equals 1, and as the graph is y equals cosine theta. So I'm going to use one simplification of sine of a plus b equals, actually I'm going to do the cosine. Cosine a plus b is cosine a cosine b minus sine a sine b. And I want to do the derivative of cosine. d dx of cosine theta is going to be cosine, let's say theta plus h minus cosine of theta over h. And that's going to be our limit. So here I'll use this formula to say cosine theta plus h is cosine theta cosine h minus sine theta sine h, and then we'll go ahead and subtract the cosine theta there. All that is divided by h. So cosine theta cosine h, h is near 0, so this comes out to be just cosine theta. Sine theta sine h is h, because this we can just replace sine h with h minus h sine theta, and minus cosine theta over h. We take cosine theta minus cosine theta, and we will have minus sine theta times h over h, which is just 1. So d dx of cosine theta equals negative sine theta in radians. And taking the antiderivative, we would have negative integral of sine theta d theta equals cosine theta. Or you might put the negative sign on this side. For the usual form of the expression, integral of sine theta d theta is equal to negative cosine theta. You can do the same thing with sine. Sine a plus b is equal to sine a cosine b plus cosine a sine b. And those are a couple of trig identities. And you could use that formula to get the integral and derivative of, the derivative of sine, or the integral of cosine.